Today's numerical is a cast iron beam section is an I section with top flange 80 mm cross 20 mm, 80 mm width, 20 mm thickness for that top flange. Bottom flange width is 160 mm and 40 mm depth for that bottom flange, and web 200 mm deep and 20 mm thick. The beam is simply supported on a span of 5 meter if the tensile stress is not to exceed 20 Newton per mm square. Tensile stress not exceed 20 Newton per mm square. Find the safe uniformly distributed load. This uniformly distributed load to find. Next, find the safe uniformly distributed load which the beam can carry and maximum compressive stress. So we have to find safe uniformly distributed load and maximum compressive stress. This is simply supported beam. This beam deflect like this. That means bottom side tensile stress comes and top side compressive stress comes. And section of this beam is this T section. This bottom flange is bigger than top flange. Now write given data. Tensile stress is not exceed 20 Newton per mm square. Tensile stress denoted as sigma T is not exceed 20 Newton per mm square. And other data are span length capital L 5 meter and other dimensions are these in this cross section. We have to find this W uniformly distributed load and second maximum compressive stress, that means sigma C maximum. Steps for this numerical is first calculate position of neutral axis for this I section, next moment of inertia for this I section about x axis, then calculate moment of resistance and calculate moment of resistance with this beam bending moment. We have to get this W. And now for sigma C maximum compressive stress calculation, with the help of bending equation we calculate this sigma C maximum. So step 1 is calculate position of neutral axis. Denoted as y bar. Y bar is equal to this. Let us denote this bottom flange as 1, wave as 2 and top flange as 3. Now y bar is equal to A1 area of bottom flange, Y1 mid distance of bottom flange from bottommost fiber, plus A2 is the area of mid wave and Y2 is the distance from bottommost fiber to mid of this wave distance, plus A3 is top flange area and Y3 is distance between mid of top flange to the bottommost fiber distance, divided by A1 plus A2 plus A3. Now A1 is from this cross section C, width of this bottom flange is 160 mm and thickness is 40 mm. That means 160 multiplied by 40, 6400 mm square is area for that bottom flange. Y1 is Y1 is this distance, mid of this bottom flange from bottommost fiber. That means this is 40. 40 divided by 2, 20 mm. Next A2. A2 is area of this mid web. This thickness is 20 and depth is 200. 20 into 200 is area for that web. (4,000 mm square is web area for that cast iron beam I section. And Y2 is distance between this bottommost fiber to mid of this web distance. That means this 40 plus 200 by 2. This is 40 plus 200 by 2. That means 40 plus 100, 140 mm is Y2. Now next A3. A3 is top flange area. Top flange width is 80 mm and thickness is 20 mm. 80 multiplied by 20. 1600 mm square is area for that top flange. And Y3 is Y3 is this distance, mid of this top flange from bottommost fiber. That means this 40 as it is, 200 as it is, 40 plus 200 plus 20 by 2. (250 mm). Put these all values A1 to Y3 values in Y bar equation. So we get position of neutral axis from bottom fiber. So A1 Y1 6400 multiplied by 20 plus 4000 multiplied by 140 plus 1600 multiplied by 250 divided by 6400 plus 4000 plus 1600 is 90.67 mm is position of neutral axis. From bottom fiber, bottommost tensile fiber. From bottommost tensile fiber, position of neutral axis Y bar is 90.67 mm for that cast iron I section. Next step is calculate moment of inertia. Moment of inertia denoted as I. So for calculation of moment of inertia, I is equal to I x1 bottommost flange moment of inertia plus web inertia Ixx2 and plus top flange moment of inertia Ixx3. Therefore, I is equal to this is x1 and for that I section neutral axis is this and this is xx. We have to calculate this moment of inertia Ixx. For that, first calculate bottom plane moment of inertia I x1 x1 axis. So for calculation of I x1 axis moment of inertia, parallel to this x1 axis is 160 dimension. 160 as it is, multiply by 40 cube divided by 12 plus area for that bottom plane is is 6400 multiply by distance between this x axis and x1 axis. Distance between this x axis and x1 axis is this much distance. Is this x axis is from bottom, that means position of neutral axis 90.67 mm. Here this distance is 90.67 mm, and this red line I x1 distance is 20 mm. So 90.67 minus 20, this whole 90.67 from bottom fiber, and deduct this small part. Because we are interested in this distance. So 90.67 minus 20 is 70.67 mm. So right here 160 into 40 cube divided by 12 plus area is 6400 multiply by distance between both axes are 70.67 and square of this distance for parallel axis theorem. This is I x1 plus so plus I x2. Now I x2 is wave moment of inertia. This wave 90.67 is moment of inertia for that I section, and I x2 is y2. Y2 is 140 mm, that means above line. Something here x2. For calculation of wave moment of inertia about x2 axis is parallel to this x2 axis is 20 mm. 20 as it is, multiply by 200 cube divided by 12 plus area 20 into 200, that means 4000 mm square, and multiply by distance between this x2 axis and x axis. Distance between this x2 distance from bottom fiber is 140 mm, and x distance is 90.67 mm from bottom fiber. That means 140 minus 90.67 is distance between both axes. This both axis distance is 140 minus 90.67 is 49.33. 49.33 is distance between both axes. So calculate 20 into 200 cube divided by 12 plus area 4000 multiply by 49.33 square plus again plus I x3 moment of inertia. x3 moment of inertia is about this axis. This top flange mid axis x3 x3. So this x3 is parallel to this x3 distance is 80 as it is multiplied by 20 cube divided by 12. So right. Plus area of the top flange is 80 multiplied by 20, that means 1600 mm square, and multiply by distance between these both axes are x3 axis from bottom is y3 250 mm. This is 250 mm, and this x axis is 90.67 mm. That means 250 minus 90.67 is 159.33 mm. And square of this for parallel axis theorem. So I is equal to 6400 multiplied by 70.67 square plus 160 into 40 cube divided by 12 is 32.82 into 10 raised to 6 plus this 4000 multiplied by 49.33 square plus 20 into 200 cube divided by 12. 23.07 into 10 raised to 6 plus 1600 multiplied by 159.33 square plus 80 into 20 cube divided by 12 is 40.67 into 10 raised to 6. Therefore, this moment of inertia for that I section is 32.82 plus 23.07 plus 40.67 is 96.56 into 10 raised to 6 mm raised to 4. Is moment of inertia for that whole I section is 96.56 into 10 raised to 6 mm raised to 4. This section is I section. Our interest to find this load, uniformly distributed load. For that, calculate neutral axis. So for that, stress distribution diagram is this much. Neutral axis is here from bottom 90.67 mm. YT tensile 90.67 and YC is 260 minus 90.67 169.33 mm YC. Here sigma C and sigma T. We have to find W. For W, use So with the help of this diagram, trace distribution diagram, write sigma c upon sigma t, this parallel triangle equal triangle theorem. With the help of this, sigma c upon sigma t is equal to yc upon yt, and in numerical we have sigma t value 20 Newton per mm square. Maximum sigma t is 20 Newton per mm square. Calculate sigma c, yc upon yt into sigma t. Yc is 169.33 divided by yt is 90.67 and multiplied by sigma t is 20. So sigma c is 169.33 multiplied by 20 divided by 90.67 is 37.35 MPa. Is sigma c compressive stress C. Our this sigma c maximum calculation is done here. For W calculation, calculate bending moment for this beam, simply supported beam. And simply supported beam bending moment formula is WL square by 8. So bending moment is for simply supported is equal to WL square by 8, and beam length is L is 5 meter, W into 5 square by 8. So 5 square divided by 8, 3.125 W is bending moment for that simply supported beam. Now, when we equate bending moment with moment of resistance, we have to find this W value, uniformly distributed load value. So for finding moment of resistance, using bending equation. M by I is equal to sigma by Y is equal to E by R. So in this numerical, we don't have E, modulus of elasticity or modulus of rigidity, and curvature, radius of curvature. So use this, only this, M by I is equal to sigma by Y. So M moment of resistance is equal to sigma by Y into I. So M is equal to sigma by Y into I. Use maximum sigma, this 169.33 mm. Maximum distance, YC distance 169.39 mm. This YC. Why YC? Why not YT? Because YC is maximum, and when we use YC, use sigma C. If YT is maximum, then I use sigma T. So M is equal to sigma C is here 37.35 is sigma C. Multiply by I is 96.56 into 10 raised to 6. Divided by YC is 169.33 MPa. Therefore, moment of resistance is equal to 37.35 multiplied by 96.56 multiplied by 10 raised to 6 divided by 169.33. This is 21.29 into 10 raised to 6. 21.29 into 10 raised to 6 kilonewton, Newton mm. Because this 37.35 is in Newton per mm square, and this value is also in mm, and this is also in mm square, so Newton mm value is Newton mm. M is equal to 21.29 kilonewton meter. So equate bending moment with M, that means moment of resistance. Bending moment is this 3.125 W equal to moment of resistance is 21.29. So W is equal to 21.29 divided by 3.125 is 6.81 kilonewton per meter. So this is uniformly distributed load, 61.81 kilonewton per meter. For that, I cross section with simply supported beam. See this I cross section total depth is 200 plus 40 plus 20. That means 260 mm total depth for that I cross section, and this cross section is cast iron, material is cast iron. Total depth is 260, bottom flange is 160 and top flange is 80 mm wide. Thickness of web is 20 mm and bottom flange thickness is more, 40 mm. So for that, and length is 5 meter. For that, neutral axis is 90.67 mm. Neutral axis comes here inside web, and inside web, that means bottom of this mid web, and moment of inertia about x-axis axis for this I section is 96.56 into 10 raised to 6 mm raised to 4. Sigma c is 37.35 MPa, and sigma t is sigma t 20 MPa. So here stress on compression side is maximum, sigma c is maximum. And why sigma c is maximum? Because this is simply supported beam, and this bottom part is tension part and top part is compression part. So compression stress on compression side is maximum, because see, material on this top side is also minimum. So stress act on this top side is maximum here as per analysis. Sigma c is 37.35 MPa, sigma t is 20 MPa, and W is 6.81 kilonewton per meter, and moment of resistance is 21.29 kilonewton meter. So this numerical is complete. Thank you very much.